Hi, I will be walking you through our work, GMC, Global Motion Corresponder for 3D point-based scene interpolation under large motion. In this paper, we tackle the problem of 3D scene interpolation. So the input would be two states of a dynamic 3D scene, each captured from multiple viewpoints. And the goal is to reconstruct and interpolate between these 3D scenes. The challenge that we identify in this paper is that when the motion is large, identifying where a point moves is challenging and non-trivial. Hence, existing methods do not do a good job. For this paper, we have assumed 3D GS as our primitives. The core challenge in scene interpolation with point-based representation lies in establishing reliable correspondences. Each point must predict its motion to a correspondent location in another frame. Most existing methods assume that the motion between adjacent time steps is small, and therefore the point position change minimally, and correspondences can be established via Euclidean nearest neighbor search. For illustrative purposes, consider this pencil, which moves a small distance. And the correspondences between the two time steps can be established easily. And here the blue lines indicate the point correspondence. Existing works fall in two paradigms. First one is deformation fields. Here, a separate neural deformation model is used to predict per Gaussian displacement. And this deformation model and the 3D Gaussian parameters are jointly optimized. Example of this paradigm would be 4DGS and deformable 3DGS. The second paradigm is iterative refinement, where point positions are iteratively refined from the previous time steps. Example for this would be dynamic Gaussians and paper in motion. Now consider what happens when the motion between adjacent time steps is large. When this happens, local neighborhood search becomes unreliable, since objects have moved far from their original positions. And hence the problem of point correspondence becomes ambiguous and ill-posed, because each point may have multiple plausible matches. For example, this is a plausible point correspondence, so is this, and so is this. Naively doing nearest neighbor search leads to implausible trajectories, which violate spatial rigidity and physical constraints. For example, in this, the end of the pencil does not have any correspondence, and if we use these correspondence to predict motion, we would violate spatial rigidity and physical constraints. Before moving on to the solution, let's take a moment to think about the properties that we would want from an ideal method. The first property would be semantic and color consistency, which means corresponding points should share appearance and semantics. The second property would be neighborhood correspondence, which means that semantically similar points should move together. And also, there should be correspondence for all points in both states. Such an ideal method would achieve accurate correspondence and be able to predict global motion. Since using just Euclidean distance does not work for the large motion setup, let's try to come up with a toy distance function that also considers the color, C, and semantic features, F, of each point. We can argue that even this distance function would not be sufficient. For example, A and B would have, point A and point B have the same color and semantic information, but under this distance function, the point correspondence would be wrong. The idea of the paper is that since it is hard to come up with a predefined analytical function, we propose to learn these correspondences through a differential optimized based method. Now we present the overview of our method. We train two 3D Gaussian models from the start state and the end state, and then we transform both sets of Gaussians into a learned shared canonical space where corresponding Gaussians occupy identical spatial locations. Here, the transformation R and T is learnable and is predicted by transformation networks, which we call unary potential fields. They are parameterized as MLPs. We define a single unary potential field F as a function that maps 3D coordinates nu and feature vectors f tilde to SE3 transformation. In practice, we use PCA projected dyno features for f tilde, and these potential fields are called unary because each time step requires individual mappings to the canonical space. The question remains that how do we train these unary potential fields? Before moving on to the loss function, consider this energy term, Eij, which uses the means of the Gaussians mapped into the canonical space. Compared to the distance function that we saw earlier, and notice that here nu hat is learnable, where previously it was not. Now we define the loss that we use to train the unary potential fields. For each Gaussian in the start state, we find a Gaussian in the end state that minimizes the energy term Eij. And for each Gaussian in the end state, we find a Gaussian in the start state that minimizes the energy term Eji. This loss encourages Gaussians that are similar in color and feature and that are close in the canonical space to be matched, which results in smooth and realistic correspondences. Notice that the loss is bidirectional. The two-way nature ensures that all points in both time steps find correspondences. And because the network is initially untrained, new hat terms do not contribute much initially. Hence, the color and feature term help establish initial soft correspondences. To further enforce smoothness and local rigidity, we incorporate a local isometry loss applied to the transformation in the canonical space. Each Gaussian GI finds its nearest neighbors in the original space and enforces that the distance are preserved after transformation. Now, once the unary potential fields have been trained, we can define the relative rotation and the relative translation as shown. The interpolating between the time steps 0 and 1 can be done using interpolating between the identity transformation and this relative transformation defined. Let's move on to the results section. Here, a dynamic 3D scene is shown. And compare the performance of our method with the baselines. While our method is able to smoothly interpolate between the start and the end state, the baselines fail to produce any realistic renderings. Here we have another dynamic 3D scene. And again, our method is able to smoothly interpolate while the baselines do not do a good job. Thank you. You can find out more about this work using the QR code and the website link mentioned.